I'm representing Qunova Computing, and I'm the CEO of Qunova Computing. So today I'm going to talk about the challenging quantum advantage with the chemical use cases for this presentation. Okay, it's moving. Okay, somehow. So the Qunova Computing is a quantum software application developer, and our mission is to bring quantum computing innovations with a quantum advantage to our customers. And our vision is we are the house for the new drug and material discovery, as well house for the AGI solutions. And so this is how we look at the evolution of the new computing innovations. So we started with the CPU, and now we are in the era of GPUs, and followed by the era of QPU. And there are so many hardware developers in this area, and we can believe that this market will take off sometime soon. And if you look at the industry, this is another computing industry. So it has a vertical integration of with the full stack of the components in the industry, so they can provide the computing services. And Qunova is focused on delivering the application quantum softwares. So I'm talking about the quantum advantage. So think about what can be definition of quantum advantage. There are many different versions, but at the end of all the discussions, it will end up with if the quantum computer can be more useful than supercomputer. So just considering that kind of criteria, what you can think about this way. So when a quantum computer can deal with a 40 qubit level problem, that corresponds to petascale computation in today's computing technology. So this is the point where actual computing happens. And if you can make use of 60 qubit level, the quantum computation, that can be really the point of driving the emergence of quantum computing market. So once you have 60 qubits, there are many opportunities to explore something new, like the new science, and also new drug designs or material designs, and also some new solutions for the industrial optimizations. And eventually, we are going to work on the AI in industry with the quantum computer. One of the most important reasons why we are going to work on this AI industry is that today's electrical power use by today's technology will grow up to 10% of the global electricity generation. So that becomes in 2030. So it becomes a very, very significant issue in growth of the industry with GPT or any other new natural language process. So you can think about when we can achieve quantum advantage. So probably most of the experts in this industry or community consider that quantum advantage will be available when the fourth Toronto quantum computer becomes available. That might be year 2028 or sometime later. But this is too far away from the point of view that how much investment has been poured into this the quantum technology development. And so actually what community is looking at is like bringing the quantum advantage with NISQ machines. So this market with the NISQ machines we should start off very soon, and then that will last longer than even after the fourth Toronto quantum computer becomes available. The reason is NISQ machines will be orders of magnitude cheaper than fault-tolerant quantum computers. So we are introducing to the market the high VQE, which is a handover iteration VQE, and followed by the family of that, like high VQA and high VQLS, and those will provide all quantum advantages and many different problems. And in order to be distributed to general public, we are trying to use the distribution channels like KissKiss or the Amazon bracket or the Azure Quantum, the cloud services. And now I'm going to talk about a little bit of technology or science. So we are interested in bringing quantum advantage in chemistry problems. So let's first look at the chemistry problem, which is just nothing but analysis of molecules. And the molecule, the energy is modeled with a Born-Oppenheimer model. And the model looks that much complicated. And I think most of you know about this model. And this is very complex model. So no direct solution can be achieved. So what you can do is you can do classical approximation to solve this one. And the meaning that the model is approximated is if there is only one electron with an electron cloud around. Then you can solve this problem relatively easily. And there are methodologies like TFTs and Hartree-Fock modeling provide this modeling. However, this is not accurate enough. So if you want to find a more accurate solution, then you have to consider many-body interactions. So there are many electrons in a molecule, and that becomes a very complex problem now. And then we call this level of modeling is a high-level quantum model, and this one solves the many-body problems in this molecule model. So and this problem is intractable, and if we can find the solution of this model very quickly and efficiently, then we can consider that that brings quantum advantages in this industry. In order to deal with the many-body problems, you have to deal with the second quantization in the quantum model. And once the second quantization is achieved, then you can convert that to a larger matrix. And once you have this larger matrix, then you can find the exact solution of the molecule model. But if you look at that, the matrix, the size of matrix is 2 to the n, where the n is the number of orbitals that you have to consider. And so it becomes a very, very difficult problem to solve. However, if you look at the matrix, there are many zeros in there. So matrix information is very sparse. So you don't have to really deal with this larger matrix. So one of the options, you can make a kind of subspace matrix, which has the same information as you can get that can provide you the same level of accurate solution. However, this is typically done on the textbook. You first have to do diagonalization, followed by the reduction of the space. This is a very, very intractable problem again. So another approach that you can think about is now you reduce the matrix size first and then do diagonalization. That's easier. But it is very difficult to find that important component in the matrix without really solving the matrix problem. So if you get help of the quantum simulation, so the quantum circuit can mimic the electron state in the molecule, then you can be smarter to select the right the matrix component, so the size of the matrix can be reduced. And then if you apply the eigensolver, the classical eigensolver, then you can find the solution of the problem. And this is, again, very accurate. So if you consider all that into, the organization of the algorithm, it will be like this one. So you have to have a QPU part which generates the quantum simulation of the molecule. And also you have a CPU part that solves the matrix. And also it must be able to reduce the size of the matrix and also solve the matrix. And then there's another part that can iterate between the two to find the optimum solution. So there is an optimizer. So if you have these three components, then you can run this algorithm iteratively, and it turns out to be very, very efficient. So if we compare the original VQE with this new high VQE, the structure of the algorithm compares like this one. And one of the notable observation here is that we get rid of all the Pauli word measurements. Okay, so this one makes the whole algorithm very, very redundant. So we got rid of the Pauli word measurement. So we make just one circuit run and then sample the states, and that information passed to the Hamiltonian solver. And then this one can create a subspace to reduce the Hamiltonian. So the problem becomes tractable. And then we just repeat this one. Okay. So it is about 1,000 times faster or even 10,000 faster than the previous VQE. And also the errors that happens in the measurement is not delivered to the classical solver. So error is a kind of blocked in this process. So we can always find the accurate solutions. So running this one, we can easily find that we can achieve 1.6 millihartz chemical accuracy, which is very, very difficult to achieve. And then this is 1,000 times faster than previous ones, and it can go beyond the 60 qubits. And then it is validated with many hardware vendors. Okay, for example, because of this one, we could do live demo at one of the exhibit show back in July in Korea. So we just ran this algorithm in front of the audience of the exhibition. And while they are talking with me, they could observe the calculation results appearing on the screen every 10 minutes. And that was a very, very fascinating result. And also live demo of quantum computation on the spot was the first live demo, actually. So this one shows some example, the results. We applied that to a chromium dimer experiment with the 24 qubit. That was an early experiment, so we could get chemical accuracies. And also we applied to lithium sulfide, the benchmark, the experiment. So this one is kind of paves the road to the development of lithium sulfur, the solid state battery development. And also we applied this one to the ion porphyrin, the molecule modeling, which requires 44 qubits in this experiment. So all these were very, very successful and all delivered accuracies. So this is a very important, observation that NISQ computer becomes available. I mean, NISQ computers becomes useful. So this can bring the market time of the quantum computing technology to the next year, probably, or year 2026. So I'm going to briefly discuss about the products at Qunova and the use cases. So we are bringing two types of products. One is Milky Way, the other is Pulsar. Milky Way is a kind of information or informatics-based the material and material design platform. And Pulsar is an ab initio type of solver. So it produces a very exact solution after creating some the molecule designs by Milky Way. And so the use cases of these products can be found in this in the following examples. So the first one is, as I discussed before, lithium sulfur battery development. We've been investigating a lot of testing on this the sulfur reduction reaction, the reaction process, and that also produces very accurate solutions with our high VQE, with using a 28 qubit level, the experiments. And also we are currently also investigating the fuel cell oxygen reduction reaction models. And as you can see here, we can also apply 24 qubit level, the quantum computing applications in this example. So we are increasing number of qubits to find more accurate solutions in this regime. Another example is like some CO2 capture is a very interesting the market sector, and actually the size of the market is approaches almost $1 trillion. And one of the important material for the carbon capture is called the monoethanolamine. And so we calculate the energy between the MEA and the carbon, the dioxide, and that calculation was successfully achieved on the with the 28 qubit level, the experiments. And as you can see here, the overall calculation converges very, very fastly. And another use case is that we looked into the material that forms the OLED, the display material, and one of the basic, the molecule architecture in there that is called dihydroazaborin, and that was we applied about 20 qubit modeling here, and this one has many different deformations. So we calculate the deformation energy and to observe the correlation coefficient, the R square of 96%. So it provides a very accurate solution again. So there are many use cases. We tested about 20 different molecules so far, up to 44 qubits, but we are going to finally uncover the results with the 60 qubit level experiments in this month or in January. So using that kind of capability, we can probably open up the industry use case. I mean, chemical industry use cases with our partners. So we first, secured the technologies with 60 qubit level, the analysis, and then this can be used first, for scoring the design of materials or chemicals by just directly applying a high VQE technique there. And also, if we just combine this high VQE with AI tools and so on, and some other screening tools, and we can provide the new material design, and also they can provide the quantum level accuracies in the design. So it will give you more higher success rate from the material designs. And so then finally we can provide customized solutions to our end product users, so that we can help them out to find to choose the best materials for their applications and so on. So all these discussions are in the beginning stage of developing collaboration with our potential end customers, and initial end customers are following. So Rhee and LG Electronics, Post Holdings, and Boreum, and those are working with us. And there are several more currently we are developing developing the use cases together. So as an epilogue, so NISQ era will be extending actually, and with the use cases with quantum advantages, until the logical qubits becomes as cheap as the physical qubits. So this is very important, I think, thinking. So where we have to invest, the technology development and also the financial investments. So because of that, we are hiring NISCO computing scientists and engineers. Thank you very much.
There is a question. We don't have lots of time, but there is one question, I think.
Hi, thanks for the nice talk. I wanted to ask what the main algorithmic difference was between high VQE and the QSCI. Is it the feedback in the initial state, or?
Right. Okay. So SCI or QSCI, I think those are kind of more the classical, method specific methodologies. So, for example. So right here, so we are introducing the subspace sampling by the quantum the ansatz, okay, and this is done in an iterative way. So typically in QSCI or SCI, you are given with the initial state, and just the classical algorithm evolves to find out the subspace, and then in our algorithm, we create that kind of subspace with sampling from the quantum state. And this quantum state evolution is more efficient than classical evolution. So, so basically, the overall architecture is we are improving SCI. And with the help of the quantum, simulation or sampling. So, and this quantum sampling is capable of producing more like entangled state samples, while the SCI, classical SCI, is not really capable of producing the entangled state from the beginning. So that kind of area is the resource that provides quantum advantage.
Cool. Thank you.
Thank you. Thank you very much,
Okay.
Dr. Rhee.
Yeah, thank you very much.